Wow, some of the questions you folks have sent in lately really get you thinking, like really thinking about the very nature of reality, the big stuff. And that's kind of what led us to this article someone sent, How Category Theory Can Reveal the Foundations of Physics. It's about this, well, pretty radical idea that some super abstract mathematics category theory specifically might actually be like the most fundamental language we have to understand the universe.
Yeah, it's kind of mind-blowing. And it's not even just this one article, and it's like this whole constellation of ideas you've all sent in that sort of connect to this. So in this deep dive, what we're going to try to do is like cut through all the complexity and really distill down to the core insights. We're going to be focusing a lot on the ideas of this guy, Urs Schreiber, who was interviewed in the article. It's sort of like we're looking for a mathematical key that can unlock the structure of, well, everything.
Yeah, like the master key to the universe, maybe? So I think for most people, when they hear category theory, they probably think it's something only mathematicians care about. But this article hints that it could be the key to solving some of the biggest mysteries in physics. We're talking about these super abstract mathematical concepts maybe being more fundamental than even space and time. I mean, that's pretty wild.
It is wild.
So let's dive in. Schreiber starts off with this idea, like a philosophical idea, about the duality of pure nothing versus pure being. He's drawing on this old philosophical idea called Hegelian dialectics. I gotta admit, that sounds pretty out there. Why is that even relevant to a discussion about, physics?
Well, you're right. It sounds super philosophical, but what Schreiber's doing is he's basically taking this very abstract philosophical concept and saying, hey, what if this is actually a blind spot in our current physics? So it's not so much about the philosophical debate itself, but more about whether our current math might be missing something really fundamental, like the very first step in describing how something can come from literally nothing.
Right, right.
So he's saying that every physical phenomenon we observe, like everything we see and experience, it exists somewhere on this spectrum between pure nothing and pure being.
Right.
And the idea is that our existing mathematical tools, even though they're super powerful, they might not be precise enough to actually describe that initial leap from nothing to something.
Not mathematically precise enough. I mean, that's a pretty bold statement when you consider that so much of physics is, well, math.
Yeah, it is.
Okay, so from this, super Zen idea of nothing and being, he then goes on to talk about the spontaneous emergence of reality. He says things like the superpoint, 11-dimensional space-time, even supergravity might actually just arise out of logical necessity. I mean, how do you even wrap your head around that?
Right. It's a really radical idea. And it sort of speaks to the power of category theory as Schreiber sees it. It's like, think about it this way. Just like 2 + 2 must equal 4 because of the inherent structure of arithmetic, Schreiber is suggesting that maybe fundamental physical concepts also have a similar kind of logical necessity. It's like with a sufficiently fundamental and robust system of logic, certain structures, maybe even the fundamental building blocks of our universe, they have to exist. They're inevitable.
So it's like reality kind of blossoming out of pure logic.
Exactly. Yeah, that's a good way to put it.
That's amazing. So to help people kind of navigate this whole world of ideas, Schreiber created this online resource called nLab. And it sounds like it's way more than just a website about category theory.
Yeah, it definitely is. So while category theory is like the central organizing principle of nLab, you can kind of think of it as like a Rosetta Stone for this, the language of the universe. It's like revealing the hidden grammar that connects all these different scientific ideas.
Yeah.
And it's super valuable when you're trying to see the big picture, right?
Right.
So it's like this giant encyclopedic lab notebook where you have insights from all these different areas of math and physics all documented and linked together using this lens of category theory. It's all about uncovering these deep structural similarities that might otherwise remain hidden.
Okay, so it's like having this map that shows how all these different areas of physics and math connect. That's really cool. Now, the article also touches on these really complex, cutting-edge areas of physics like non-perturbative quantum field theory and M theory. And it mentions how these fields are kind of hitting a wall, running into these major roadblocks. Schreiber argues that these aren't just like minor technical issues, but a sign that maybe we're missing the right language, the right concepts to even ask the right questions in these fields.
Yeah, that's a really crucial insight. He's suggesting that in these very advanced areas of physics, we've essentially hit a wall. And it's not because we don't have enough computing power or we don't have enough experimental data, but because the way we're thinking about these problems, the language we're using, is inadequate. It's like trying to describe, I don't know, a symphony, using only the language of basic musical notes.
Right, right.
You can get some of it, but you're missing the richness and the complexity of the relationships between the notes, the harmonies and the rhythms and all that.
Bubble structure.
Exactly. And Schreiber believes that category theory can provide that richer language that we need. It allows us to focus on relationships and structures in a way that our current mathematical tools might not fully capture.
It's really fascinating how he draws a connection between all this and philosophy. He mentions this post he wrote on Philosophy Stack Exchange about how, historically, philosophical ideas have often paved the way for huge breakthroughs in the hard sciences.
Yeah, that's a really interesting connection. And it's this historical pattern that Schreiber is pointing out. A lot of the core concepts in math and physics, they actually started as philosophical inquiries. Think about the debates around infinity, the nature of space and time, even the idea of what constitutes a proof.
Right.
These are all things that philosophers were grappling with long before they became formalized into mathematical systems. And the real power emerges when you can translate a philosophical intuition into a rigorous mathematical framework, because then you can reason about it precisely and you can develop these incredibly powerful tools.
It's almost like philosophy provides the spark, and then math builds the engine.
That's a great way to put it.
That's awesome. And Schreiber specifically points to the Hegelian dialectic, the whole being nothing and becoming thing, and how this abstract concept actually finds this concrete mathematical formulation in topos theory and category theory, and that's pretty mind-blowing.
Yeah, it is.
Okay, so this brings us to this kind of technical-sounding idea of cohesive infinity toposes. Can you explain what those are in, relatively simple terms, and why are they so important in this whole idea of finding a new language for physics?
All right, let's try to unpack that. So cohesive infinity toposes, they're basically this super advanced mathematical framework that comes out of this intersection of category theory and modal logic. And modal logic, just very simply, it's a way of reasoning about what's possible and what's necessary. So you can kind of think of cohesive infinity toposes as these incredibly sophisticated mathematical spaces that have this built-in sense of connectedness or smoothness. But the key insight here is that these aren't just abstract mathematical objects. They're actually providing physicists with new tools to describe some of the most fundamental aspects of reality.
Wow. Okay.
Specifically, they offer new ways to understand these things called generalized differential cohomologies, which are pretty complex mathematical tools for understanding how different aspects of a physical system are connected and how they change. It's kind of like they allow you to track not just the individual properties of something, but the relationships between those properties in a very precise way. And this is really important for advanced theories like string theory and for understanding the fundamental forces of the universe.
So these cohesive infinity toposes are like the mathematical tools that Schreiber thinks can help us map out the universe's journey, as he puts it, from nothing to something to everything. I mean, that's a pretty big claim.
It is a big claim. But he's really emphasizing that this isn't just speculation. He's saying that by using these very advanced mathematical frameworks, especially these cohesive infinity toposes, we can actually trace this emergence of the universe in a very formal, rigorous way. And he's saying that these aren't just potential descriptions, they're like provable, rigorous facts within this mathematical system that actually align with what we observe about the universe.
So it's like the structure of this really abstract math is actually mirroring or maybe even underlying the fundamental processes that created everything.
Exactly, yeah.
And that brings us back to this really powerful metaphor that Schreiber uses, the universe as emergent logic. What does that really mean for us, in the context of everything we've talked about?
I think the essence of this metaphor is the idea that the universe wasn't really assembled from pre-existing parts, right? Instead, it kind of spontaneously emerges from the inherent structure and necessities of logic and mathematics itself. So imagine pure nothingness as this, ultimate blank slate. And then you have these fundamental principles of logic, like the first brushstrokes on that canvas. They start to define relationships and structures on that slate. And it's not random, it's according to their own intrinsic rules. And then this process, which is driven purely by logical necessity, it keeps going and going and eventually gives rise to this whole complex web of space-time and forces and particles that we observe. So the profound implication here is that logic isn't just some tool we use to try and understand the universe. It might actually be the very engine that powers its existence.
So logic isn't just describing reality, it's creating reality.
Yeah, that's the idea.
Yeah.
Mind-blowing, right?
Yeah. So if we bring it all together, what we've learned from this deep dive is that math and philosophy aren't just these separate fields. They're actually deeply intertwined, especially when we're trying to unlock the deepest secrets of reality. And maybe the next big breakthroughs in physics won't come from building bigger particle colliders or doing more experiments, but from developing entirely new ways of thinking, new conceptual frameworks based on these really abstract areas of mathematics like category theory.
And for someone like you, who's always looking for these deep connections between seemingly disparate ideas, this really highlights the power of exploring even the most abstract concepts, because they might actually hold the key to understanding the very fabric of reality.
Definitely gives you a lot to think about. Like, if the universe really does emerge from this fundamental logical necessity, what are the limits? What are the possibilities baked into that structure? And what other, seemingly abstract fields of knowledge might be hiding similar keys to unlocking the mysteries of existence? I mean, it really makes you question the very nature of logic, mathematics, and reality itself.
Yeah, it really does. It's a whole new way of looking at the universe.
Absolutely. Well, on that note, we're going to wrap up this deep dive, but keep those questions coming, folks. We love tackling the big ones. And who knows, maybe one of you listening out there will be the one to crack the code of the universe. Until next time.
Thanks for listening, everyone.